Question 1. The intensity of the sun's radiation at the position of the Earth's orbit, which is the solar constant, is approximately 1.4 times 10 to the 3 watts per metre squared. Just rewrite that. 1. Explain why the average solar power per square metre arriving at the Earth is 3.5 times 10 to the 2 watts per metre squared. There's a mistake there. So explain why the average intensity when it reaches the Earth's surface is actually only 350. Okay, I'm going to give you a long explanation for this, so bear with me, okay? Before I explain, I really want you to write the following sentence into your notes, and this is something I want you to take with you at all times. The average intensity of solar radiation at the Earth's surface is 1/4 of the solar radiation, or the solar constant. I want you to remember that. I don't think it's really said anywhere in the notes, so I want you to remember that, and I'm going to tell you why before I answer number 1. So we've got the Earth here. It has a radius of r, and we have radiation coming in from the sun. Like this. It says the solar constant is 1,400 watts per metre squared. So as it's reaching the Earth from the sun, it's giving 1,400 joules per second per metre squared. But on the Earth, it's only receiving, the average, on the Earth's surface is only receiving 350 watts per metre squared. So why is that? Well, there's 2 reasons. I'm going to change colour for this. Reason number 1 is that the surface area of the Earth is 4 pi r squared. It's a sphere. So the whole surface area of the whole Earth is 4 pi r squared. But if you imagine this radiation coming from the sun, it's actually really only going to be incident on a disk, like a 2D disk that's facing this radiation. That's really how much of the Earth can actually absorb or receive this sunlight. And the area of this disk is pi r squared. So actually, only a quarter, because this is a quarter of that, only a quarter of the Earth's surface is available to receive this radiation. So it can only receive a quarter of the solar constant. If you think about it another way, I'll change pen again. This radiation is hitting the Earth's surface like this. When it hits at the centre here, it has maximum amount of transfer of energy from the radiation onto the Earth, or it has a maximum effect. But if you go to the top of the Earth or the bottom of the Earth, you can see that the angle by which the radiation makes with the Earth is quite acute, which means a smaller component of the radiation is actually hitting the Earth at a normal, which means it's less effective, right? So if we look at the intensity and how that's related to angle, the intensity is related to cos square theta, and that is roughly equal to a half. So the intensity from the sun, 1,400 watts per metre, is already just halved because of the angle that it meets the Earth's surface. But you're saying, wait a minute, but it's reduced by a quarter. Why is that? Well, this whole half here doesn't receive any radiation at all, does it? So actually, when you do a half times a half, then it's a quarter. So there's 2 reasons that the average intensity of solar radiation at the Earth's surface is a quarter of the solar constant. But let's answer this question now, and we'll use the first reason because it's easier to explain. So question 1, explain why the average solar power per square metre arriving at the Earth is 350 watts per metre, which is a quarter. Okay, the solar radiation received by Earth as if, stumbled over my words there, as if it were captured by a disk with the same radius as the Earth. And that the area is pi r squared. Okay. This captured energy is spread out over the entire surface of the Earth. And that area is 4 pi r squared. Therefore, when averaged, the intensity is reduced by a factor of 4. Factor of 4. Now, what I would like you to do is I would like you to embrace that very long explanation. And I would like you to write it down in your revision notes, okay? I suggest a good place would be the common diagram section and use a diagram I've given you here, or just the other notes section and learn from past papers. I suggest you learn that explanation off by heart. It comes up quite a lot, and I don't think it's particularly clear in the actual teaching of the course. Question 2. State why the solar constant is an approximate value. Well, let's think about this. This is the sun, this is the Earth, and the Earth orbits the sun. But actually the Earth orbits the sun almost in an elliptical shape rather than a circular shape. So sometimes the Earth is quite far away from the sun, and that means the solar constant is less. And sometimes the Earth is quite close to the sun, and that means the solar constant is greater. When you average out over the year, then the solar constant is 1,400 watts per metre squared. But at certain times of the year, it's actually greater or less because the Earth follows an elliptical path. The Earth follows an elliptical path around the sun, meaning the solar constant is averaged. Another thing to take into account is the sun itself. The sun itself obviously radiates out energy, but it goes through something called solar cycles. It doesn't give out exactly the same amount of energy at all times. It tends to go in sort of cycles. It gives out more energy at some times, less energy at other times. So solar cycles is another reason why the solar constant would be averaged or not constant, because the sun actually gives out different amounts of energy rather than when it's received at the Earth. But I would say the main reason for this is the elliptical path. And question 3. Photovoltaic cells are approximately 20% efficient. Estimate the minimum area needed to supply an average power of 850 kilowatts over a 24-hour period. Okay, well, we know that on Earth, each metre is receiving that amount of power. Okay, so each metre on Earth gets 350 watts. We want to produce 850,000 watts. So how many of them do we need to make that? Well, it's really simple. We do 850,000 divided by 350, which gives us 2,429. That's the amount of output energy we want. That's the amount of input energy, but we know that this is only 20% efficient. So actually we have to divide that by 20% to get the actual value, which is 12,143 meters squared. So we need 12,143 square meters of photovoltaic cells to give out 850 kilowatts. Question 2. The property of the molecules of greenhouse gases which leads to their ability to absorb infrared radiation is, and we've got resonant frequency, speed of rotation, total electric charge and diameter. What actually happens is we have these molecules like methane or nitrous oxide or water, and they oscillate. They oscillate as though they're attached by a spring. And the resonant frequency of these molecules is very close to the wavelength of infrared radiation, or the frequency of infrared radiation. And it's that property that calls them a greenhouse gas and allows them to absorb and then rescatter. So the answer is A. Question 3. Gases in the Earth's atmosphere are believed to be responsible for the greenhouse effect include, well, the 4 gases we've got in our syllabus are CH4, which is methane. So that's good and that's good. The other one is water, which is H2O. That one and that one. The other one is CO2, which is carbon dioxide. And the final one is N2O, which is nitrous oxide. So our answer is D. Question 4. The Sun has a radius of 7 times 10 to the 8 metres and has a distance of 1.5 times 10 to the 11 metres from Earth. The surface temperature of the Sun is 5,800 Kelvin. We'll draw a little diagram here. So that's the Sun. It's giving out radiation. It has a temperature of 5,800 Kelvin. It is 1.5 times 10 to the 11 metres away from Earth. And it has a radius of 7 times 10 to the 8 metres. Show that the intensity of the solar radiation instant upon the upper atmosphere of the Earth is approximately 1,400 watts per metre squared. Okay, let's look at the luminosity of the Sun first. The amount of energy it's actually giving out is the Stefan-Boltzmann constant times the surface area of the Sun times temperature to a power of 4. That's how much it's giving out here. How much is actually then received by the Earth depends on how far it is away from the Earth. You can see that the Sun is giving out radiation in all directions, and we only want it in one direction, here at the Earth. So we have to divide that by the surface area of the sphere of this sphere here. And I think we have everything we need there. Oh, actually, no, we haven't got the area here, and that's the surface area of the Sun, and the surface area of the Sun is 4 pi r squared. So let's change this equation. 4 pi r squared t to the power 4 over 4 pi d squared. We can cancel these 4 pi's out. What we're actually looking at now is the Stefan-Boltzmann constant times the radius of the Sun squared times the fourth of the temperature divided by the distance from the Sun to the Earth, all squared. Let's pop in all of our numbers. Stefan-Boltzmann constant is 5.67 times 10 to the minus 8 times the radius of the Sun, which is 7.0 times 10 to the 8 squared, times 5,800 to the power 4, divided by the distance from the Sun to the Earth, which is 1.5 times 10 to the 11, all squared. And that gives us a value of 1395.5 watts per metre squared. And we, of course, approximate that to 1,400 watts per metre squared. That question comes up a lot. I've just looked at number B. And I think we're going to use what we learned in the question 1. The albedo of the atmosphere is 0.3. So the Earth is here. It's got the atmosphere here. 1,400 watts per metre squared is incident from the Sun. But the albedo is 0.3. That means that 0.3 of this is scattered back, which means that 0.7 is actually going through. So the actual amount that's coming through the Earth's atmosphere is 1,400 times 0.7, which gives us a value of 980 watts per metre squared. Do you remember what happened before? We said, but to average out over the whole surface area of the Earth, we have to divide by 4. We have to take a quarter of that. So we take a quarter of 980 divided by 4, and that gives us 245 watts per metre squared. So when you take into account the Earth's atmosphere and the entire surface of the Earth, the actual proportion of the solar constant that's received on the surface of the Earth is averaged out to 245 watts per metre squared. C. Estimate the average surface temperature of the Earth. We have to think of the Earth as a black body. And what that means is all the radiation instant on the Earth is absorbed and then re-emitted. So there's 245 watts per metre squared instant on the Earth, and that's re-emitted because it's a black body. So we can use this formula here. L equals Stefan-Boltzmann constant T to the fourth. And we want to find out what T is. We know that L is 245 watts per metre squared because whatever absorbed is then re-emitted. We know that the Stefan-Boltzmann constant is 5.67 times 10 to the minus 8, T to the fourth. So we can find out that T to the fourth is equal to 245 divided by 5.67 times 10 to the minus 8, which is equal to a big long number, 4.32 times 10 to the 9. And the fourth root of that gives us T is equal to 256.4 Kelvin. And let's approximate that down to the right number of significant figures. Everything is given at most to 3 significant figures. So the average surface temperature of the Earth is 256 Kelvin. I love that question. Question 5. The average albedo of glacier ice is 0.25. Okay, that means if this is ice, 0.25 is reflected or scattered back, which means that 0.75 is absorbed. Okay, what is the ratio of the power absorbed by the glacier ice, 0.75, divided by the power reflected by the glacier ice, so 0.25. 3 over 4 on the top, 1 over 4 divided by a quarter, which gives us 12 over 4, which gives us 3. The answer is D. I was just trying to do that without a calculator. Haha, look smart. The key here was to realise that the power absorbed is 0.75 and put the right numbers in. Question 6. A solar farm is made up of photovoltaic cells of area 25,000 metres squared. The average solar intensity falling on the farm is 240 watts per metre squared, and the average power output of the farm is 1.6 megawatts. Calculate the efficiency of the photovoltaic cells. When we're looking at efficiency, we want to look at the total amount of energy in and the total amount of energy out. So let's look at the total amount of energy in. And of course, I'm saying energy, but actually we can translate that to power as well, because power is simply the energy per second. The two terms can be used interchanged here. We've got 250,000 metres squared on this farm, and each metre is 240. So the total energy in to this farm is 240 times 25,000. Total amount of energy in, therefore, is 6 times 10 to the 6 watts, which is 6 megawatts. And we can see that the total energy out, or total power out, is 1.6. So the efficiency equals 1.6 divided by 6, which gives us a value of 0.27, and that translates, of course, to 27% efficient. That's actually quite efficient. Question 7. A hydroelectric system has 4 250 megawatt generators. The specific energy available from water is 2.7 kilojoules per kilogram. determine the maximum time for which the hydroelectric system can maintain full output when a mass of 1.5 times 10 to the 10 kilograms of water passes through the turbines. Before I go any further, I'm just going to quickly explain what a hydroelectric system is. What you have is you have a body of water at a height. And it could be a reservoir, a loch or whatever in Scotland it would be. And this body of water falls through that height through pipes. It goes through pipes, and what it does is it turns a turbine. That turbine obviously goes round, and by moving round we have magnets moving through a coil of wire, and it generates electricity. That's not really necessary for the question, but just so you understand what a hydroelectric system is. And what we're saying is, this water up here, the amount of energy we can get out of water is 2.7 times 10 to the 3 joules per kilogram. And we have 1.5 times 10 to the 10 kilograms of water. So the total amount of energy we can get out of this system is, let's put energy equals 2.7 times 10 to the 3 times 1.5 times 10 to the 10. And that gives us a value of 4.05 times 10 to the 13 joules. That's the total amount of energy that's available to the system using that mass of water. This mass of water goes down the pipes and generates electricity. And the generators have 250 megawatts, each of them, and there's 4 of them. So what we want to do is we want to say this amount of energy that's available for the water. We know that each generator can give out 250 megawatts, which is joules per second. So we've got 4 times 250 times 10 to the 6. That's how many seconds are available from that mass of water. And that gives us a value of 4.0 times 10 to the 4 seconds. And of course we want to turn that into hours because it's not particularly useful having that in seconds here. So we divide it by 60 to turn it into minutes. Then we divide it by 60 to turn it into hours. And that gives us 11.1 hours. So this system will generate electricity using that mass of water for 11.1 hours. Before we look at C, let's just remind you, this water here is stored at a height, which means it has gravitational potential energy, mgh. It's all stored up there and it's ready to flow down the pipes and turn into electricity using the generators at the bottom. And C says, not all stored energy can be retrieved because of the energy losses in the system. Explain one such loss. At this stage, it's only 1 mark, but you do not just want to give the answer of friction. It's not detailed enough. Let's imagine this water has to go through the pipes. We don't have to imagine, it does, it has to go through the pipes. And if you imagine the water going down the pipes, there's going to be friction at the side of these pipes. So one of the answers could be friction between the water and pipes. And what will that do? Well, it will turn some of that potential energy into heat energy. Turns gravitational potential energy into heat energy, which is not the kind of energy we wanted to turn it into. So that's one of the losses. Another one could be, okay, let's go down to the bottom of the system. This water is turning the turbine here. Okay, the water turns a turbine. But you'll notice after it's turned a turbine, this is a turbine here. I know it's a terrible diagram, but there we go. The water comes down, whoosh, 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 and then it whooshes away. So it's got kinetic energy here. It turns a turbine, which turns it into electrical energy. But some of the water then whooshes away. Okay, so another reason that not all stored energy can be retrieved is because the water leaves the generator at speed after turning the turbine. This requires the wastewater to have kinetic energy. So not all of the stored energy is turning into electrical energy. Some of it is retained as kinetic energy in the water. D. At the location of the hydroelectric system, an average intensity of 180 watts per meter squared arrives at the Earth's surface from the sun. Solar voltaic cells convert this solar energy with an efficiency of 22%. The solar cells are to be arranged in a square array. Determine the length of one side of the array that would be required to replace the hydroelectric system. Well, we know that the hydroelectric system is giving out 4 times 250 megawatts of energy. That means it's giving an output of 1,000 times 10 to the 6, which is 1.0 times 10 to the 9 watts of energy. Okay, let's look at the other side of this. So we know that each square meter on Earth is receiving 180 watts per meter squared from the sun. But we know that the solar cell or the photovoltaic cell is actually converting only 22% of that. So whilst it's receiving 180 watts, it's actually only giving out 39.6 watts every square meter. So how many square meters do we need to give out that much power? Well, it's 1.0 times 10 to the 9 divided by 39.6, which gives us 2.5 times 10 to the 7 square meters. And what that looks like is this, right? The area is 2.5 times 10 to the 7 square meters. But we only want one side. We want to know what that is. So what we do is we take the square root of it and we say the square root of 2.5 times 10 to the 7 equals 5025 meters long. And how many significant figures should we give this to? To 2 significant figures. We're going to say it's 5,000 meters or 5 kilometers is the length of one side. Question 8. The satellite carries an experiment that measures the peak wavelength emitted by different objects. The sun emits radiation that has peak wavelength of 509 nanometers. The peak wavelength of the radiation emitted by the Earth is 10.1 micrometers. Determine the mean temperature of the Earth. Okay, we're going to head to our data booklet and we're going to look out this equation. The maximum wavelength times temperature is equal to 2.9 times 10 to the minus 3. We know that the maximum temperature of radiation emitted by the Earth is 10.1 micrometers. So we've got T equals 2.9 times 10 to the minus 3 divided by 10.1 times 10 to the minus 6. And that gives us a value of 287, and that's always in Kelvin. If you wanted to change that into degrees Celsius, we would do 287 minus 273, which gives us 14 degrees Celsius. I personally would probably just keep it in Kelvin. Question 2. Suggest how the difference between the peak wavelength of the sun and the peak wavelength of the Earth helps to account for the greenhouse effect. And this is 3 marks. So the first thing we'll notice is that the peak wavelength of the sun is less than the peak wavelength of the Earth. The sun is 5.09 times 10 to the minus 9 meters, and the peak wavelength of the Earth is 1.01 times 10 to the minus 7 meters. So the wavelength of the sun is less, which means that the frequency of the sun's radiation is greater. That's the first thing we'll notice. The second thing we'll notice is that the infrared spectrum has wavelengths ranging from 700 nanometers, or 7 times 10 to the minus 9, all the way up to 1 millimeter, so 1 times 10 to the 3. And you'll notice that the peak wavelength of the sun is just outside this range here at 5.09 times 10 to the 9, minus 9. But the Earth's radiation, the peak radiation, sits within this infrared spectrum. Okay, so why is that important? 3 marks. Mark number 1. The wavelength of the sun, and when I'm saying the wavelength of the sun, I mean peak wavelength of the sun, is less than the wavelength of the Earth. It does not fall into the range of infrared radiation. Number 2, the greenhouse gases absorb radiation within the infrared spectrum and resonate, re-emitting this radiation. Number 3, the radiation is emitted or scattered in all directions, which is back to the Earth, including back to the Earth, heating it up. And of course, more of those greenhouse gases means that more radiation is absorbed and re-emitted, which means it gets hotter. So that's why greenhouse gases are not such a good thing, especially those man-made greenhouse gases. C. Not all scientists agree that global warming is caused by the activities of man. Outline how scientists try to ensure agreement on a scientific issue. Well, what a scientist would do is they write a paper. So they publish a paper. And they tend to collaborate with each other. Maybe you've heard of something called CERN in Switzerland. It's a particle accelerator there. And scientists from all over the world come and collaborate to talk about the results and make sure that they're all on the same page. Once they've published a paper and they collaborate, they encourage other scientists to repeat the experiments. So experiments are repeated. And if all results end up being repeatable, then actually you can say, well, this is an agreement. I've tried it, I've discussed it, we've looked at the paper, I agree, and that's how we agree on a scientific issue. Question 9. 3 gases in the atmosphere are carbon dioxide, dinitrogen, monoxide, and oxygen. By the way, sometimes this is called nitrous oxide, you might see that. Which of these are considered to be greenhouse gases? Well, we know from the syllabus that methane, nitrous oxide, water, and carbon dioxide are the greenhouse gases. So our answer here is 1 and 2A. Question 10. Light of intensity I0 is instant on a snow-covered area of Earth. In a model of this situation, the albedo of the cloud is 0.3 and the albedo for the snow surface is 0.8. What is the intensity of the light at P due to the incident ray? So we can see that the light bounces off the snow and then bounces off the cloud. What is the intensity? Well, it starts at I0, and when it hits the snow, 0.2 of that I0 is absorbed and 0.8 of the I0 is reflected. So 0.8 of the I0 is then directed towards the cloud, at which point 0.3 of the 0.8 of the I0 is reflected and 0.7 of the 0.8 of the I0 is absorbed. We're interested in this. So 0.3 of 0.8 is 0.24 I0. The answer is B. Question 11. The moon has no atmosphere, and that's why it's a terrible place to go for a party. Boring. And it orbits the Earth. The diagram shows the moon with rays of light from the sun that are instant at 90 degrees to the axis of rotation of the moon. A1. A black body is on the moon's surface at point A. Show that the maximum temperature that this body can reach is 400 Kelvin. Assume that the Earth and the moon are the same distance from the sun. If the Earth and the moon are the same distance from the sun, then we know that the solar constant of radiation from the sun is 1,400 watts per metre squared. To make this easy, let's assume that our black body is 1 meter squared. That takes the area component out of this equation for us. So we head to the data booklet and we have this equation here. We know that the radiation received by the sun at this point is 1,400. We know that this is a constant, the Stefan-Boltzmann constant, so it should be really easy to adapt this to find out the temperature. 1,400 divided by 5.67 times 10 to the minus 8 is equal to 396 Kelvin, and which of course is approximated to 400 Kelvin. Now in the mark scheme I know that it says the solar constant is 1360 watts per meter squared, but you can see that it doesn't really matter, it's given us the same answer here. And the syllabus does say use 1400 as an average solar constant. Remember we talked about earlier this tutorial that the solar constant is averaged because of the various factors that happen out throughout the year. A2. Another black body is on the moon's surface at point B. Outline without calculation why the maximum temperature of the black body at point B is less. Let me redraw it here. That's B and that's A. Let's have a think about this radiation as though it's a beam of light from a torch. Think about point A. This beam of light from a torch is going to be incident on the moon's surface at A, and it's going to give us a little small circle. If we take that same beam and it's incident on a point at B, that circle is going to be bigger because it's spread out, which means the energy at point B is spread out over a larger area than at point A. That means that the intensity from the same radiation is less at B than it is at A. And if the intensity is less, if that's less, this is the constant, then the temperature must be less as well. Therefore, temperature at B is less. B. The albedo of the Earth's atmosphere is 0.28. Outline why the maximum temperature of a black body on the Earth when the sun is overhead is less than point A on the moon. Let's look at the moon and the Earth. This is the moon, this is the Earth, and our black body is here. They're both the same distance away from the sun according to this question, which means they both receive 1,400 watts per meter squared from the sun. What's different? The Earth has an atmosphere, and that atmosphere reflects back 28% of the solar radiation, and it only transmits through 72%. So actually only 1,008 watts per meter squared get through the atmosphere. And if there's less radiation being transmitted through, the temperature is less. So the temperature of the black body on Earth is less because only 72% of the radiation from the sun transmits the atmosphere, whereas the moon does not have an atmosphere.